Welcome to the third video in this series about graphing trigonometric functions. Here we'll look at the graphs of secants and cosecant. Let's take a look at the cosecant. It turns out the cosecant graph looks like this, and ultimately you're just going to have to memorize this and accept it on face value so that you can graph other cosecants. But before we get to that, let's take a look at a few key features of this function and to why it sort of looks the way it does. First of all, it has a local minimum at pi over 2, 1. You'll notice if you plug in pi over 2 into the function, you do in fact get a value of 1. It turns out, as far as positive numbers go, the cosecant can't get any lower than that. Similarly, there's a local maximum at 3 pi over 2 negative 1. Let's talk a little bit about this asymptote. There is no defined value for the cosecant of pi. You'll remember that the cosecant of pi is 1 over the sine of pi, which is 1 over 0. But 1 over 0 doesn't exist. And so in some sense there's a gap right there at pi and 2 pi, and it turns out all multiples of pi. Let's look into this a little further. If we were to look higher up on the graph, we would notice that the graph itself and the asymptote are getting closer and closer together, which is characteristic of graphic asymptotes. And just to get a little bit of a sense as to why that's happening, I have picked a random number, or not so random number, on the x-axis here, slightly to the left of pi. Let's analyze that particular portion of the graph. Now for that particular value of x, there is a corresponding point on the graph, and it turns out to be quite high up. I believe it's about 4 or 5 spaces up as a y coordinate. And what's causing that to happen? Well, imagine that I picked a number really close to, but slightly to the left of pi, maybe 0.93 pi. If I were to compute this, the sign of something slightly to the left of pi turns out to be a very small decimal. In fact, the closer I get to pi, the closer that decimal gets to 0. And because you may remember from middle and early high school that dividing by a small number produces a very large answer, that explains why this point is so high up and why the graph reaches so high and essentially goes up forever without getting to that undefined asymptote. By the way, this works out to be about 4.5 or 4.6, which explains the height. But one can imagine that if I were to pick even closer points to pi, say 0.99 pi, I could get a pretty large value. That explains why the graph is so almost infinitely steep at that point. Ultimately, however, whether the logic there made sense to you or not, you have to memorize the cosecant function, because the purpose of this video is to graph variations on the cosecant with some transformations. So let's look at the secant as well. First, we just saw the cosecant looks like this. Before we go on to the secant, it's a good time to remind you that this is just the graph of the cosecant that you see here from 0 through 2 pi. If we were to expand the view of the graph, we would see that there are other sort of U-shaped things, for lack of a better word, that propagate infinitely in both directions. It turns out the secant graph has a somewhat similar look to it, and you can see it in the upper right corner here. Now I won't derive and go through the key features of the secant as I did for the cosecant, but one thing that's worth noting here is that the secant, and while it has sort of a different look, the reason it does is because we typically look at it from 0 to 2 pi, and when we broaden our view, as you can see on the bottom of the screen here, that there are really just an infinite number of U-shapes going in both directions for the secant, as we saw for the cosecant. In fact, even though, and here are the two graphs you'll memorize, but even though these two memorizable graphs have somewhat of a different appearance, They're really not that different. On first glance, though, they are. The cosecant on the left looks like it has two U-shapes. When we look at it from 0 to 2 pi, it does. Whereas the secant on the right looks like it has one U-shape and two half U-shapes. But again, that's because we look at these from 0 to 2 pi, which is the tradition in trigonometry. When you look at a wider angle here, you can see that the cosecant and the secant, one's in blue and one's in green. And you can imagine which one is which, but the bigger picture here is that they're both just an infinite number of u's, and the only difference between the secant and the cosecant is that one is shifted pi over 2 spaces to the left or right of the other one. But all that is the big picture. What we need to focus on now is these are the two graphs you memorize, and you'll be asked other questions involving secant and cosecant with some transformations, and we'll apply our transformation strategies to graph these newer functions. So now let's look at a specific example. Let's graph y equals -2 times the cosecant of 3x. Here's the graph of y equals cosecant x. You might see it here in light gray. Because we're graphing a function based on a function we've memorized, all we have to do is understand and know the transformation rules. So what you're going to see here is less about trigonometry and more about the rules of compression and stretching. So let's start with this 3 here. Because of this 3 here, there's going to be a horizontal compression by a factor of 3. What does that mean? Well, that means that, for example, the local minimum of cosecant, which occurs at pi over 2, is going to be compressed into 1/3 of the distance to the y-axis, or pi over 6. The asymptote for cosecant, which would normally be at pi, is going to be compressed into 1/3 of that distance, 1/3 of pi being pi over 3. Next, for example, the local maximum of cosecant, which occurs at 3 pi over 2, is going to be compressed in 1/3 of the distance to the y-axis, which works out to pi over 2 if you do the pi algebra, 1/3 of 3 pi over 2. And lastly, the asymptote at 2 pi is going to be compressed into 1/3 of its distance to the y-axis, or 2 pi over 3. And it's worth briefly noting here that it isn't just the asymptotes and local maxima and minima that get compressed into 1/3 of their distance. It's literally every point on the graph, but we're just tracking the important ones here. Now that's the effect that the 3 is going to have. And just as we learned in transformations, this negative is going to have a reciprocal effect in the sense that it's going to flip over the x-axis. The 2 is going to cause a vertical stretch. Everything's going to stretch away from the x-axis. Ultimately, if you piece all those clues together, you will discover that your cosecant graph is right there. And if you're a little confused at this point and didn't track all of that, I can't say that you honestly were supposed to track every detail there. But the bigger picture is what matters here. If you understand the horizontal compressions and stretches and vertical compressions and stretches that you learned in the non-trigonometric graphing situation, then you can apply those same things by just memorizing the graph of secant and cosecant and applying those exact same rules to these specific functions that you have memorized here. And while we won't do any more examples today through this video, the general idea, I hope, is conveyed. Memorize the secant and cosecant, and then simply do compressions and stretches and other shifts to modify from the memorized secant and cosecant to the secant and cosecant that you're trying to graph. And that completes the third video in this 5-video series. Thanks for watching.